Hello everybody. Today we are going to solve this problem of the day, complement of a base 10 integer. So given an integer, let's say 5, we want to flip every bit, like if it is 101, we want to complement that to 010, and we want to tell the number which is represented by this bit pattern. Like for 7, if it is 111, the complement is 000, so it represents 0. So let's see. So let's say I'm given 101, okay, and this is in base 2. What if I take the knot of this and flip every bit? I will get 010. But the problem with this approach is, let's say it's an int data type. Usually this is represented in 32 bits. So 101 is kind of represented as 0000, and then in the end 101. Now how many zeros do we have? We have, I think, 29 zeros. We have 29 zeros and then a 101. If we flip this or take the knot of this, we get 010, but then all of these are 1. 29 ones, I guess. And in and we represent numbers in 2's complement representation. So if the most significant is 1, then the number is considered as negative, and in 2's complement, and this is considered to be in 2's complement representation. In order to get the positive number equivalent to this, we have to first flip this and then add 1 to it. Like for example, let's see, if I'm given 7, in order to find minus 7, we have to, if this is 111, we have to first flip this and then plus add 1. So like, yes, this has a lot of zeros in front. So let's consider there is only 1 0 in front. So 10001 is considered as the 2's complement representation of minus 7. Of course, I can add any number of zeros in front. That will not change my answer, because let's say if this is known, is my answer. If I add one more, imagine this is considered as the negative bit, like 0 1 2 3 4 5. So this is minus 2 to the power 5, and this used to be minus 2 to the power 4, but now it has become plus 2 to the power 4. So difference of 2, like 1, I have given out 2 to the power 4. So imagine if this is 1001, then if in 2's complement representation, this is 0 1 2 3. So minus 2 to the power 3 plus 2 to the power 0. So this represents 7, or minus 7 in our case. So if we do 1 1 0 0 1, we added one more. So now this is the negative bit. So minus 2 to the power 4, 2 to the power 3, 2 to the power 0. So again, so minus 16 plus 7 plus 1. So this is still minus 7. Sorry, plus 8 plus 1. So this is still minus 7. So this is the way how 2's complement representation works. So if this is the number, I have proven that it does not matter how many ones I have in, as long as the most significant bit is 1. So that means 1010, if this is 2 to the power minus 3, because 0 1 2 3, then this will be minus 7, because 2 to the power minus 3 is minus 8 plus 1, or in this case, yeah, I think we started with 5, yeah, so it will be plus 2, so minus 6. This is not what we want. We want just 0 1 0, and not something in the front that is ruining my answer. So we want to restrict our scope. We can restrict our scope by first finding the most significant bit. Like for example, if 101 is given, this will be the most significant bit. We don't care about any leading zeros. and we can only toggle up to this. So, okay, this is toggle this, toggle this, toggle this, and I have reached the most significant bit, so this will be my answer. Cool. So there are two ways of finding this most significant bit. Either I can go from the end and try to AND it with 1, and I check when is the last time I ANDed with 1 and got some positive value. Okay. Or we can use a library function called count leading zeros in C++. So let's first try to do it the normal way. So we will try to calculate this int MSB. Let's consider that as 0. Of course, let's say so for bit equal to 0 equal to, I guess, 32. I think the answer is up to 10 to the power 9, so 31 bits are enough. Plus, and I check if this one right shift bit times like this gets me one shifted up bit number of times right shifted, and if I AND it with my and I get some positive value, then I can say that MSB equal to bit. Okay, now I know the MSB. Of course, if MSB is 0, then we return 1. Otherwise, we toggle up to the MSB. So let's just use this. Now I will only go up to MSB, and I will only toggle up to. Now in order to toggle, we just do the same idea, but we just XOR. N equal to 1 right shift n XOR with n, or I can just say n XOR equal to this. Okay, so XORing kind of flips the flip. The XORing with 1 flips the bit, and we can return like this one. It's okay, this will be bit plus plus. Yes, this is working. Let's try to submit. In case of 1, so the MSB will be 1. I output it 1. Let's see. Okay, let's try to. Okay, if if MSB equal to 0, no. If n is 0, then we only return 1. MSB 0 can be even n is equal to 1. In that case, also MSB will be 0. No? Silly mistake. So the idea is go up to the MSB. I think if you don't do this, probably this will still get accepted. Let's try. But this can have a bug, like this gets still accepted. So the idea is go up to the MSB, do the toggling part. After that, we don't care. There is a short trick to finding this MSB. So we can just say that, say, let me toggle this. There is a function called count leading zeros. So you can say the int MSB equal to, in our case, since we are dealing with integers, so 31 minus underscore underscore built in CLC. So this gives me the most significant bit. Like this will count me the number of leading zeros, and my 31 minus this is my answer. But this creates a problem when this n is 0. If when n is 0, then the number of leading zeros, it's kind of like forever. So this is a problem. So we must handle that. So if n is equal to 0, 0, this MSB function will return something weird. So we want to ignore that case. So we must handle it this time. Other than that, it should work. Yeah, I guess it. Yeah, I have to handle. Oops. So I have to handle that before I send in this function. So basically, this function kind of fails if n is equal to 0. Okay, so this works. I hope you understood. Have a great day, and I would love your feedback.